Okay, let's continue the discussion of section 6.2, one-to-one functions and inverse functions. Okay, so section 6.2, one-to-one function. Inverse functions. Okay, so we already discussed the definition, some examples about inverse pairs, inverse function and its original function, and the properties of them. And now let's try to study the graph of inverse function from the graph of the original function. So first, the theorem. Theorem says the graph of a one-to-one function f, and it is one-to-one, so it has an inverse, and the graph of its inverse f negative 1 are symmetric with respect to the line y equal to x. Okay, so the graph of the one-to-one function and the graph of its inverse are symmetric with respect to the line y equal to x. Y equal to x is a diagonal of the first and the third quadrants. So this is line y equal to x. Then the graph, the theorem claims the graph of the one-to-one function and the graph of the inverse function are symmetric. Okay, so why? The reason is that, remember here, once you have a point on the graph of the original function, assume this is point AB. When x is equal to a, y is equal to b, so b is fa. B is fa, it implies a is f inverse of b. So a is f inverse of b. So it means when you get input b for the f inverse, then you get output a. So AB is on the graph of original function, then BA will be on the graph of the inverse function. And these two, if you connected them, they are symmetric with respect to the line y equal to x. So y equal to x is a perpendicular bisector of this segment. Okay, so that is the meaning of the theorem. Okay, so let's see the example. How do we use this to find the graph or solve the problems related to the graph? Okay, so the graph is the one of one-to-one function, a one-to-one function y equal to fx. Draw the graph of its inverse. Okay, so what does it mean? It means here you have a given graph. Let's see what it is. It's a 1, 2. Here's a negative 1. Here's a negative 2. This is 1, 2, 1, and 2. So the graph is here's a 2, 1. And here's a negative 1, 0. Here's a negative 2. Here's negative 1 and 1, 2, and negative 2. So this is a graph of this one-to-one function. It's one-to-one. Why is one-to-one? You use horizontal line to intersect the graph. You have at most one intersection point. So here it has 1. Here it has nothing. Here it has nothing. Here is 1. It's always at most 1. So this is the graph of one-to-one function. We only know this. We don't care about the formula. We want to sketch the graph of the inverse. How do we sketch it? First, you need the line y equal to x. So y equal to x. You get a 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. So you get this line. 0, 0, of course. Y equal to x, just repeat it, coordinates. 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2, okay? And when you have 2, 1 here, check this. You have AB, then you switch the order, you get BA. So 2, 1 is on the graph of the original function. Then 1, 2 will be on the graph of the inverse. So 1, 2, 1, 2 is here. This is 1, 2. Let me use 1, 2. This is a point on the inverse. And this part, it is a negative 1, 0. X is negative 1, y is 0. So its counterpart will be 0, negative 1. 0, negative 1 is here. It's a 0, negative 1. It's on the y-axis. X-axis is x coordinate is 0. Y coordinate is negative 1. And this point has a coordinate negative 2, negative 1. Then its counterpart will be negative 1, negative 2. Okay, just switch the x and y. Okay, and then you connect the segment. Okay, so this red line is the graph of the inverse. The red line is the graph of the inverse. Okay, and this intersection point must be on the line y equal to x. Whenever your graph of the function and the graph of the inverse intersect, then this intersection point must be on the line y equal to x. Okay, so that's the graph and the graph of the one-to-one function and the graph of the inverse. Okay, so now let's find a way to find the formula of the inverse. So how do we find the formula? We start from y equal to fx. This is a one-to-one function. The step 1, exchange x and y. And step 2, solve y in terms of x. And after you solve it, you will get y is f inverse of x. So that's it. That's it. Okay? So let's see. We start from the simplest example. Find the inverse of fx equal to 2x plus 3. Okay, and draw a graph f and f inverse on the same coordinate axis. Okay, so let's see. First, you get y is equal to 2x. Y is equal to 2x. That's original function. Then you exchange x and y. You get x is 2y plus 3. X is 2y plus 3. And you solve y. In terms of x. Okay, so how do we solve y? So we move 3 to the other side and divide the equation by the coefficient of y. So this is F inverse. This is F inverse. So exchange, solve. Okay. So now let's verify the theorem. Graph F and F inverse on the same coordinate axis. So let's put it here. Okay, let's see. First one, let's graph, this is fx. First, when x is 0, y is 3. X is 0, y is 3. This point, 0, 3. When x is negative 1, you see, when x is negative 1, negative 1 times 2 is negative 2. Negative 2 plus 3 is 1. Okay, this point. So this is the graph, because this is linear function. Linear function is always a straight line. The graph is a straight line. So this is y equal to fx. And y equal to f inverse of x. F inverse of x is here. When x is 0, y is negative 3 over 2. When x is 0, y is negative 3 over 2. Negative 3 over 2 is here. Negative 3 over 2. When x is 1, y is negative 1. When x is 1, you got 1 half. 1 half minus 3 halves is negative 1. Here. X is 1, y is negative 1. It's here. Okay, so if we extend it a little bit, they will intersect. And now let's try to sketch the graph, sketch the line y equal to x, y to x. Okay, so almost. If I don't use a pencil, I can get a better graph. You will see that this is these two graphs are symmetric about the line y equal to x, and the intersection point should be on this y equal to x line. We almost get to the intersection. A little bit error. Okay, so that's the first example. So the steps are very simple. You exchange, solve. So exchange is not a difficult job. To solve it sometimes will take some effort. Okay, so let's see another example to for this type of problem. So example, let y equal to fx equal to 2x plus 1 over x minus 1. Of course, here x is not equal to 1. When x is 1, denominator is 0. And this function, we assume it is 1 to 1. F is 1 to 1. Well, of course, we can prove it. but let's just claim it is 1 to 1. Find its inverse and check the result. Okay. So two jobs: find the inverse. Second, check the result. Okay. To find the inverse, we have two steps, remember. First, you exchange x and y. So first, you find x is 2y plus 1 and y minus 1. So this is a exchange step. And second step, you solve y in terms of x. Okay, so we multiply this equation by y minus 1. So the left hand side, it becomes xy minus x is 2y plus 1. We're going to move 2y to the left side, negative x to the right side. So okay, so the left hand side, all the terms contain y. The right hand side, all the terms do not contain y. So you factor out y. And you divide this equation by the coefficient of y. And then this is f inverse of x. Of course, here the domain is that x is not equal to 2. The original function has a domain x is not equal to 1. This function has a domain x is not equal to 2. Because when x is equal to 2, the denominator is 0. Okay, so we finished the first part of the question. Find the inverse. Check the result. What does it mean, check the result? You compose f inverse with f, see if you get x. Okay, so we did this type of computation last time. Now let's do it. F inverse compose with fx. Compose with f of x is f inverse of f x is 2x plus 1 over x minus 1. Okay, now let's see. The computation is a little bit tedious. So f inverse of x is x plus 1, x minus 2. So whenever you see x, you use this complex formula. So 2x plus 1 over x minus 1. This is x and plus 1. 2x plus 1, x minus 1, and minus 2. So this is our formulation. And we are going to simplify it, see if it is equal to x. So how do we do this simplification? We are going to multiply top and bottom by x minus 1. I want to use this factor to cancel the denominator from top and the bottom. Okay, so this term times the first, it becomes 2x plus 1. 1 times x minus 1. You just consider this as a one quantity. 1 times x minus 1 is x minus 1. And similarly, you multiply this term with the first rational expression, you get 2x plus 1. And minus 2 times it, x minus 1. Okay, so we'll continue to simplify. Plus 1 minus 1, they canceled. 2x plus x is the 3x, so the numerator is the 3x. And denominator, let's see, 2x plus 2, plus 1, minus 2x. Minus minus is plus 1, plus 2, plus 2. So 2x, negative 2x, it cancels. So the denominator is 1 plus 2, 3. 3 cancel 3, you get x. So this, from here, you get the result x. It completes the check problem. Check the result means you compose it with fx, f inverse with f, you get x. So this is the check part. Okay? So we finish this example. Of course, you can check the other one. It's not necessary. Okay. Let's see another example. find the inverse of y equal to fx equal to x squared if x is greater than or equal to 0. With this condition, this function is 1-to-1. X squared function is 1-to-1. Without x greater than or equal to 0, it's not 1-to-1. It does not have a inverse. And graph f and f inverse. Okay. Okay, so let's see. So we have this function. The first step, we exchange x and y. And then we are going to solve y in terms of x. Here we will take square root. But remember, this x is greater than or equal to 0. X squared is it doesn't matter x is positive, negative. X squared is always greater than or equal to 0. So y is greater than or equal to 0. Here y is greater than or equal to 0. This place is also greater than or equal to 0. And this y is the original x. This x is the original y. Okay? So the range is the original domain, and the domain is original range. So y corresponds to x. When we take square root, y has to be positive. So we take positive square root. We take positive square root. It's because this y, the range depends on the domain of the original stuff, original function. Okay, so y is square root of x is f inverse. Because this place this y corresponds to the number in the domain of a y equal to fx, original x. So the domain is a positive, so you take positive square root. And of course, here you take the square root, this x is greater than or equal to 0. This x is in the domain of f inverse. The domain of f inverse is the range of the f. It's also positive. So that's the correct answer. And sketch the graph of f and f inverse. So graph it. Okay, so when x is 1, y is 1. When x is 1/2, y is a quarter. So it's here. When x is 0, y is 0. So it's y equal to x squared. And the other one, square root of x, you see here. When x is 1, y is 1. When x is a quarter, 1/4. When x is a quarter, square root of 1/4 is 1/2. It's here. This point is 1/2, 1/4. And this point is 1/4, 1/2. And 0, square root of 0 is 0. So it's like this. And 0, 1, they determine the line y equal to x. So again, the two graphs are symmetric with respect to the line y equal to x. This is always correct. Okay, so this completed the section 6.2. In the section 6.2, we studied the inverse functions, and we know how to graph. We know the relation between the graph of inverse functions and the graph of the original functions. And we know how to find the inverse function. 2 steps. Exchange x and y, solve y in terms of x. Okay? Okay, so we still have time. Let's continue the discussion. We will back to the section 4.3. We will summarize the properties of quadratic functions. So quadratic functions and properties. Okay, so we already know that if we have a linear function, then this represents a straight line. Its graph is a straight line. And the linear function is a polynomial with degree 1. So we increase the degree, we will have quadratic function, the polynomial of degree 2. A quadratic function is a function of the form fx is ax squared plus bx and plus c. Of course, we want it have second degree. So here we require, first of all, where a, b, c are real numbers, and a is not equal to 0. Okay? A is not equal to 0. B and C can be 0. B and C are free to be 0. And because this is a polynomial, the domain is the set of all real numbers. No requirement. Just every real number can give you can be used to define the quadratic function. Okay, the domain is a set of all real numbers. Okay, and quadratic polynomial or quadratic function will have a graph. We call it a parabola. Okay, so the graph is possibly looks like this. It's called a parabola. The graph of a quadratic function. So first, we want to see how to sketch the graph of this parabola. What is the essential point or the key point we need to determine the parabola? So first, we start from the example, the simplest example. Y equal to x squared. Y equal to x squared, we can see it. Because this is x squared, so all the values are positive, so that's why we only use the upper half space. We don't use the bottom. Okay. 1x is 0, y is 0. 1x is 1, y is 1. 1x is 1/2, y is a quarter. Remember, we have that. 1x is 2, y is 4. 2, 3, 4. When x is 3, y is 9. 5, 6, 7, 8, 9. Possibly that's the highest point I can label. So good. So it increases very fast. And it's an even function. Even function means it's a symmetric about the line y-axis. So you get a similar point, symmetric point, actually. Symmetric point. It's like you open your arm upward. Okay. This is a graph y equal to x squared. If we want to sketch the graph y equal to 1/2 x squared, what it is? So when x is 0, y is 0. When x is 1, 1 squared is 1 times 1/2 is 1/2. It's here. When x is 2, 2 squared is 4 times 1/2 is 2. When x is 3, 3 squared is 9. 9 times 1/2 is 4.5. 1, 2, 3, 4, 4.5 is here. So it's like this. Again, it's a even function. So you have here, and 1, 2, 3, 4 here. Okay, so this is a y equal to 1/2 x squared. And if you want to sketch the graph y equal to 3x squared, 3x squared. Well, let's see. X is 1. 1 squared is 1 times 3 is become 3. 1, 2, 3. It's here. Well, we don't know what, we don't have enough space to label. You see here, when x is 2, 2 squared is 4. 4 times 3 is already, what is 12? Our highest label. This is 9. It's not 12. 8, 7, 6, 5, 4, 3, 2, 1. Yeah, 12 is too high. So if we want to demonstrate, it's possibly like this, or here. It's again the even function. Okay, so that's the graph y equal to 3x squared. Okay, so what is a property? So they are always open up. They call it opens up. If the coefficient is smaller, it's wider. So y equal to ax squared. Here we say a positive. A is smaller. The graph is wider. A is bigger. The graph is narrow. It's narrow. Okay, so that's the idea. So if you have a 10, you will if you have y equal to 10x squared, possibly you will look it looks like a straight line, straight up, much more steep up. Okay, so that's for the positive coefficient times x squared. If you have a negative, you basically just flip it down. Negative, you are going to flip the graph down. So this, we call it opens down. It opens down. Okay? And it starts from this point. And this point, it doesn't matter, it's a positive, a negative. They are both called the vertex. And we can always see that the y-axis is a symmetric axis, the axis of symmetry. The axis of symmetry. Here's the same thing, the axis of symmetry. So a parabola can be opening up or opening down, will have a vertex, will have a axis of symmetry. It will be narrower or wider, depending on this coefficient A. If the opposite value of coefficient A is bigger, so it's much more narrow. If the opposite value of A is smaller, it's much more wider. The opening is wider. Okay, so that's the simplest, the simple case when y is ax squared, no b, no c. Okay, so how do we sketch or determine the graph when we have b and c? When we have b and c, let's use the example first, and then we discuss the abstract formula. So assume we have fx equal to 2x squared plus 8x and plus 5. It's a quadratic polynomial, quadratic function. We want to find the graph, and we want to see the vertex and the axis of symmetry. Okay, so graph it, find the vertex and axis of symmetry. Okay, so how do we do that? We'll copy it here. We are going to go through the complete square process. So what is a complete square process? So first you leave the constant term aside and just consider the x term. X term, if it has coefficient, you factor out coefficient completely. Factor out coefficient. If it has sign, you also factor out the sign. And then recall that we have a plus x squared is a squared 2ax plus x squared. You can write a squared first or x squared first. It doesn't matter. You see here you have x squared 4x. 4x is a 2 times 2x. So x squared plus 2ax. So a is equal to 2. Then you miss a is equal to 2. So you miss a squared, you miss 2 squared. 2 squared is 4. Okay, so artificially you add this 4 here. 4 place a squared. But 4 it has a coefficient 2. You see here, you put it inside the parentheses. So 4 times 2 is 8. You add 8 in fact. You add 8, you need to subtract 8. To balance it. So here you add 4 times 2, you add 8, minus 8. You cancel 8, 8. You still have the x term, and 5. Okay? And then coefficient 2 is 2. X squared plus 4x plus 4 is x plus 2 squared. 5 minus 8 minus 3. Okay? So we have, you can call it fx or you can call it y. Okay, so how do we get the graph of this? How do we get the graph? In order to get the graph, remember we have the shift method, the shift idea. When you have y equal to fx minus h, h positive, move to right, h unit. h negative, move to left, absolute value h unit. Remember that? Okay, so we first, step 1, we get 2x squared. And then we get 2 times x minus negative 2. Remember, we always need minus. So you get a negative h, so it means you are going to shift the graph of 2x squared to the left 2 unit. So what is the process? So you have this first process, and move to the left 2 unit, 1 unit, 2 unit. So the axis of symmetry is also shifted to the left 2 unit. It becomes negative 2. Move to the left, it's minus, it's negative. Move to the right, it's a plus. Okay? And second, if you have fx plus k, if k is greater than 0, move upward k unit. If k is less than 0, move down ups value of k unit. Right? So this is the vertical shift. Okay, so let's continue. We already reached this is a 2x plus 2 squared. We already reached the 2x plus 2 squared. So we have this we have this graph. This graph is it's like this. This is axis, x equal to negative 2. The axis of symmetry. You move the y-axis to the left, and then it's minus 3 means you're going to move it down 3 units. Just move this parabola down 3 units. Move down 3 units. Negative 3. This is negative 2. Okay. It's very huge. Whatever. It's a demonstration. Okay, so that is the process. We can use horizontal shift plus vertical shift to sketch the graph of the a general quadratic function. And from here you see that the vertex, what is the vertex? The vertex is negative 2, negative 3. And the axis of symmetry is x equal to negative 2. X equal to negative 2, this line, this vertical line. Okay, so that's the example to find first the graph, the quadratic function. Second, find the vertex and the symmetry, axis of symmetry. Okay, then this is an example. We can make the computation very abstract. Abstract. It's not that concrete with numbers. So the following computation will be latter computation. So we start from ax squared plus bx and plus c. And remember, first we complete square. We factor out the coefficient and we leave c alone because c does not contain x. And then we apply that 2ab trick. Remember here, we apply this 2AB trick in order to determine what A is. So you see 2, the whole thing times x. This is a second letter. So you're going to add this number squared. This number squared corresponds to number 4. 4 is 2 squared. Copy C. You add this number. This number has coefficient A, so you have to subtract A times this number to balance the computation. You cannot change the expression. You just modify it, but you cannot change the value. Okay, then then this is a complete square, x plus b over 2a square. This part, if you simplify it, you see this is a b squared over 4a squared. The square is a b squared over 4a squared. A squared, they're cancelled. You have only 4a. And this term, you multiply top and bottom by 4a. It's a 4ac minus b squared. Okay, so anyway, if you have a number, you know how to do that. And this is the latter computation. From here, you see this -3, this -2, they are from this shift. You see, here you have the shift. This is the vertex x coordinate. -3 is the vertical shift. So when you get the number, you must get a negative sign. Here is a plus. So you get the vertex is negative b over 2a minus negative b. And this is the vertical shift, either up and down. So it's 4ac minus b squared over 4a. Sometimes this formula is complex to memorize. So what is the formula? This quantity is exactly the value of the function at negative b over 2a. You see here, you let x be negative b over 2a. X is equal to the negative, then the sum is 0, so this term disappears. You only have this. So when you get a negative b over 2a, you can evaluate the function at this point. You will also get the y value. Okay, so this is a vertex. You can use either of the formula. And let's call this is h, this is k. And the axis of symmetry is x equal to negative b over 2a. The axis of symmetry is just x equal to the x coordinate of the vertex. X coordinate of the vertex is a number in the axis of the symmetry. And the function, this function, you see here, we call this h, this k. The function fx is a times x minus h. Be careful, the negative sign, the minus, and plus k. So once you get this step, it looks like this, and you use the horizontal shift, h unit, vertical shift, k unit properly. It depends on the sign of h and k. You will get the graph of the general quadratic function. If a is positive, again, a positive, it opens up. A negative, it opens down. A positive opens up. A negative opens down. Okay? So the whole summary is on page 292. You can check that. Okay, let me write here. A positive open up, a negative open down. Okay? Let's see the example. Let's see one example. Assume we have this function fx is equal to negative 3x squared plus 6x and plus 1. Okay, so find the vertex and axis of symmetry. Okay, so, and the second question, does it open up or down? Two questions. Two questions. So we don't want to graph it. We just want to use the formula to determine. Vertex. Vertex is negative b over 2a, f negative b over 2a. Negative b over 2a, f negative b over 2a. Okay, so b is a 6, negative 2. A is negative 3. Be careful here. A, B, C all contain the sign. Minus means the coefficient is negative. Okay, so what is this? So 2 times negative 3 is negative 6. 6 with this negative sign 6. 6 over 6 is 1. So you have f of 1. So we just quickly compute this quantity. We get 1. Okay, so we get 1 f1. F1 you let x be 1. When I have x equal to 1, the negative 3 plus 6 and plus 1 is 1, 4. So this is the vertex. The vertex is 1 and 4. And the axis of symmetry is x equal to 1. X is equal to 1. And because this a is negative, you see here negative 3 as a coefficient of x squared. The graph opens down. Okay, so that is the example for the vertex and the axis of symmetry, and also we can determine it's open up or open down. Okay, we stop here today, and we will continue next time for more practice of the quadratic functions and its graphs. Okay, thank you.